Alright guys, let's solve this problem. So this is from Beer and Johnson from the chapter 16. This on kinetics of solid body. So I have chosen this problem because this problem actually introduces a lot of concepts. It is actually fairly straightforward to solve. So it focuses more on the physics rather than focusing on the mathematics or the other things that sometimes we get deviated. Not necessary, but it focuses more on the physics. It's less on the maths. So but it's very good. So let's do that, right? So over here we have a body, we have a rod like this. Now on this, and this is of course 1 meter in length. Now on this body is applied a force in this direction, E, that's equal to 2 Newton. The mass of the body is 0.8. Now this is the positive x direction. We have a few points identified on the body, that's point A, point B, and let's also assume a point C right in the middle of the body, right? So then the question is that when this force is applied, what is the acceleration? And by that we mean the absolute acceleration of point A and the absolute acceleration of point B. So we have to describe as an answer. The first one is acceleration of A vector, and B, acceleration of B vector. Okay. Now the first thing to look at this problem is to simply apply Newton's second law, right? One more thing to notice, of course, is this is a frictionless horizontal surface. So if you simply apply Newton's law, F equal to ma, what do we get? And I'll explain why we can simply apply that, right? 2 Newton is equal to 0.8, and we are doing it in the x direction. So 2 Newton is of course in the positive x direction, which is this. 2 Newton is equal to 0.8 into A, so of course A is equal to 2.5 meter per second square I cap. Now you must be wondering, how can we do that? So because we apply Newton's second law generally to a point mass, or only when the force itself is acting at the center of mass itself, right? So for example, if the force were acting at exactly this point, the body would not have any rotation. It would just go just plain translation motion. It would not have any rotation. We could just work with Newton's second law. But how can we apply Newton's second law in this case also? And what does that exactly mean? So this acceleration is of what point? So is it of the whole body, or is it of a particular point in the body? So let's get into that. And for that, we'll just have to briefly discuss system of particles. We'll briefly sketch that out and will not take much time over there. Okay. So if we have a system of particles like so, this is a XYZ reference frame. Let's make some particles over here quickly. So we have M1, M2, M3, M1, M2, M3, on which we apply forces F1 vector, F2 vector, and F3 vector. These are all arbitrary. And let's define the position vectors of these points, these particles. We have R1 vector, we have R2 vector, we have R3 vector. Of course, this is n particles, but we are just representing by 3 particles. So the net force over here is what? So net force is simply F1 vector plus F2 vector plus F3 vector. Let's say the center of mass is somewhere at this position, and it's represented by R vector. We can write R vector is equal to sigma mi is equal to 1 to n divided by m. Of course, m is equal to sigma mi, right? Now to this equation, we take m to the left side. We have mri is equal to sigma is equal to 1 to n miri vector. Now we differentiate that twice with respect to time, and we have MA vector, MAI vector is equal to I is equal to 1 to n mi ai vector. We can do that, of course, because if this is the position vector, then v vector is equal to dr vector by dt vector, and of course a vector is equal to d2r vector divided by dt2. Because of that, we can simply differentiate twice and we get the acceleration. Now from this we can then say that well, of course, f1 vector is equal to m1a1 vector, f2 vector is equal to m2a2 vector. Therefore the right hand side of this equation becomes f1 vector plus f2 vector plus f3, etc. Right, and this is ma vector on the left hand side. Now what is a vector? Now a vector is quite obviously the acceleration of the center of mass point that we drew over here just now, this point, right? This is the vector that we differentiated, right, twice with respect to time. So therefore is the acceleration of exactly this vector. This is the center of mass vector, right? But center of mass position vector. And what is m? M is the complete mass taken together, right? So of course this is quite simply Newton's second law, isn't it? So that's F net vector is equal to ma vector, meaning that the complete mass of the system can be assumed to be concentrated on the center of mass, and if we apply F is equal to ma, then the a over here gives the acceleration of the center of mass. So let's now come back to a problem and let's apply second law, and we will then get the acceleration of the center of mass if we apply F is equal to ma. So if we apply F is equal to ma, and what is center of mass? This is of course this middle point, that's point C, and if we apply Newton's second law, the net force is 2 Newton, the weight is 0.8 kg, and we have A is equal to F by m. Quite simply that's 2 by 0.8 is equal to 2.5 meter per second square. So AC is equal to 2.5 meter per second square in this direction. Okay, so now we have been able to get AC from this. How can we now work towards finding out AA and AB? So this is AA, this is A, and this is point B, this is point C, and this is of course AC is equal to 2.5 meter per second square. Okay, now of course the force being active, the force, because it's acting over here, the body does undergo a certain amount of rotation. Now because of that, when a rigid body undergoes rotation, what happens is that every point in the body undergoes rotation about every other point. So let's now do one thing. Let's now fix a reference frame on the point C itself. So we have, this is point C. So to this we attach a reference frame, right? This point A. So the point A is undergoing pure rotation about the point C, right? And if the body has got an alpha, angular acceleration of alpha, and it's got an angular velocity of omega, then we can say that acceleration of A is, of course, there's two parts to it, right? There's centripetal acceleration, there's tangential acceleration, right? That's A. This is of course in the reference frame of C itself. So AA by C is AA by C tangential acceleration plus AA by C radial acceleration, right? And of course AA by C tangential is simply alpha r, right? And A by C radial is of course omega square r, where omega is the angular velocity of the body. So we have, this is AT and this is AR, where A is basically acceleration of A with respect to C, right? So in order to get the absolute acceleration of A, what we do is we add this acceleration of A with respect to C to the acceleration of C, right? So we have acceleration of A is equal to acceleration of C plus acceleration of A with respect to C. And like I said, acceleration of A with respect to C is simply the acceleration of A with C sort of fixed and A undergoing pure rotation about the point C, and the pure rotation is divided into two different kinds of acceleration, which is tangential and centripetal acceleration. The tangential acceleration is simply alpha r. Alpha is the angular acceleration, and the radial, the centripetal acceleration, is omega square r. We know that from simple kinematics, right? So we have AA, which is now let's do one thing. Let's write the vectors over here. So let's resolve that. So AA is equal to 2.5i plus alpha r, and of course r is 0.5 because the length of the body is 1 meter, so half of that is 0.5. Alpha 0.5. This is of course also I cap because this acceleration is acting in the positive I direction. That's the tangential acceleration of A with respect to C, right? And then we have omega square r. Of course this is minus j cap, right? Because this is acting exactly like this in this direction downwards. It's acting from the direction of A towards C. That's, you know, in the minus j direction, of course. And of course we know that omega is actually 0 or tending towards 0, because this whole setup, this problem is when the force is just applied on the body. At that point the whole body is just about to start a rotation, so omega is very nearly 0, so we can assume that it's 0. So we can just neglect that part of the acceleration. So we have AA vector is equal to 2.5. So we have 2.5 I cap plus alpha 0.5 I cap, right? That's our equations. Of course, if we get to know alpha, we'll get to know the absolute acceleration of point A, right? So how do we do alpha, right? So for that, let's apply Newton's second law for rotation, right? So what's that? That's of course tau is equal to I alpha. Because these are vectors, tau is a vector and alpha is a vector. So of course for that again we'll have to choose a reference frame. So we'll attach a frame over here to the central point C, to which we'll apply moments. So we have tau acting in this direction, and because the force over here is P, which is at a distance of 0.5, the tau is 2 times 0.5 tau, right? So tau is 2 into 0.5 is equal to 1 Newton meter, right? Now what is I? I is 1 by 12 mr square. That would be 1 by 12 into 0.8 into 1 square is equal to, and that would be 0.067. Okay, so we have tau is equal to I alpha. So we have 1 is equal to 0.067 multiplied by alpha. Alpha is equal to 14.9 radian per second square. Okay, now let's apply that back into the formula. We have AA. Let's apply it over here. We have AA vector then equal to 2.5 plus 14.9 times 0.5. That's approximately 15. So that's 2.5 plus 7.5 is equal to 10 meter per second square. Similarly, we can find out the acceleration of point B. That would again be acceleration of point C plus acceleration of point B with respect to C. And of course this again would have two components. One, because B is undergoing pure rotation about c, so we would have a centripetal acceleration omega square r from p towards c pointing inwards, and would have a tangential acceleration is equal to alpha r. Of course, the former, that is the centripetal acceleration omega square r, would be 0 because omega is 0, because this motion is just about starting. So therefore the only acceleration would be alpha r, right? So let's just do that. So AC would be, of course we already found out AC, which is 2.5 I cap. So with respect to the point C, the point B is location is negative 0.5, right? So it would be 14.9 times minus 0.5, that would be 2.5 minus 7.5, that would be minus 5 meter per second square. That means this is the direction in negative x direction. That's the acceleration of point B. Okay, so let's draw out these accelerations. Let's see where that takes us, right? So we have acceleration of point B, that's 5 in this direction. We have acceleration of point C, which is 2.5. This is 2.5, nearly half of that. And we have the acceleration of point A, which is 10, right? So if we join these points together, right, so this is 10, this is 2.5, and this is 5. Now if we join these points together, we have something very, very interesting, okay? The first thing to observe over here is that when we join these points together, we'll get a straight line. And secondly, this point, right, this is actually the point which is called as the instantaneous center of rotation, meaning that about this point the complete body is undergoing pure rotation. This point is instantaneously, that is at that particular instant, at rest. It does not have any velocity, and the whole body is undergoing pure rotation about this point. So if we, let's say, want to find out the acceleration of, let's say, this point, we simply multiply, we just simply do alpha r, where this is r and alpha is the alpha of the whole body, and we can get alpha r as the acceleration, the absolute acceleration of this point. So this is also the concept of IC over. So I hope you found this problem helpful. Wish you good luck.